Yeah, Pavana, I think you can start.
Hello, everybody. Today I'll be presenting a paper that was recently accepted at NIPS. The title is PartialFed, Cross-Domain Personalized Federated Learning via Partial Initialization. This paper is basically from authors from Huawei. And thank you to the authors for providing a few of the slides in my presentation today. Here's a brief outline of today's presentation. I will first speak about the motivation, then I will explain the main concept of this paper, which is the partially loaded federated learning. Then I will explain some experiments, then I will conclude the paper. So federated learning, as we know, is a very common paradigm these days, which is used for distributed learning, mainly because of the advantage it holds in terms of data privacy, mainly because the clients can use their own data sets without sharing it with the parameter or the central server, and to do a local training to train a global model as such. So here is a brief training process, which is extracted from the most famous federated learning paper, which is the federated averaging, where the clients usually download the initialized model from the server. They do the local training on their own data sets without sharing the data sets, but they only upload the imported model parameter to the gradients, which are aggregated in the server, the central server or the parameter server. And the aggregated global model is then broadcasted down to all the clients. And this process continues until convergence. While this federated learning is very popular these days, there is the main problem that it involves is the heterogeneous data distributions of all the clients. So mainly because all the clients which participate come in with their own data sets, so the distributions may be completely different from each other, but yet they try to train one single global model. So this can lead to some degradation in performance. So it is really hard to maintain the accuracy that we wish to have. So the more famous aspect of federated learning, which is researched on these days, is the personalized federated learning, where the clients can follow the same federated learning paradigm, but instead of having a universal model, they can have a more customized model, which is applicable to their data set. For example, in this figure, we see that each of the clients have very different data sets. Like this one has an image classification data set, this has an object detection and data set with more animated objects, and this is more of a self-driving car identifying the objects on the road kind of data. So they have such different data sets, yet they will be able to use federated learning to come up with a customized model. Most of the recent works in the personalized federated learning domain has been mainly where client selection has been different, or the other approach, which is very popular, is the meta learning or regularization, where a regularization parameter can be included in the objective function to make sure that the model being trained becomes more personalized and more customized to the local client, or the parameter decoupling, etc. So these are some of the more popular types of personalized federated learning that are in practice these days. So while this is very popular, the question that we should ask is, are all these parameters useful to us? Do we need all the parameters that all the clients share at every round to the server? And should we download the same model and use all of the parameters again? So it seems like it probably is really not necessary. In fact, doing so can usually cause kind of a negative transfer, where if you have multitask problems, when you have multi-domain data sets, at all some extremes, the predicted distributions can be very different from the source and the destination. So which means that the classifier you will use at the source may really not be helpful in doing the prediction for the target data. In tasks like classification or detection, we can see that this kind of can act in a negative way. So one observation to solve this kind of a problem can be observed from what the multi-domain learning papers do. So what it's a general conclusion that we can obtain from it is that or not all parameters should be shared, because they're not necessary. In fact, they cause some negative problems in terms of the accuracy results. And there could be some domain-specific parameters which may be really useful, which probably should be involved in the training. So keeping these two conclusions in mind, this paper proposes a method called PartialFed, which is a partial initialization which follows for the federated learning paradigm. It follows mainly the main skeleton of the federated learning as such, but because there may be some parameters which can cause a negative transfer, it tries to initialize the local models with partial parameters. Why initializing with partial parameters, I mean that in federated averaging, let's say at round 1, the server sends the aggregated round 1 or any rounds, the server sends the aggregated global model to the clients. So all the clients will download the whole model and use that as the initial model for the local training. So for any global round for the local training, it usually uses the global model as the initial model. So instead of doing that, this paper proposes that instead of using the whole global model, we can probably initialize this initial model with some other partial parameters, which can be more specific to the client. And so it can be a combination of the local model and the global parameters. So this is what this paper is trying to do. But how do you know what are the partial parameters which are helpful, which are useful, and how do we select them? That's the question that should be answered. But before I jump into how this paper tries to select parameters, I will first give a main overall idea of the algorithm that this tries to follow. Then I'll substitute it with the specific methods it uses to solve the problem. So on the server side, pretty much all the steps that we do for Fed averaging or the normal federated learning remains as is. We first initialize a global model at random, and for each iteration, we try to send the global model to the clients. The clients will do their own local device training. And once the server receives all the local models from the clients, it does an aggregation and it sends it again. So this process repeats. So on the server, things remain the same. So what happens on the client side in this paper? So the first step, once the clients receive the global model, it will also load the WT-1C. C here is the client, T is your iteration, your global iteration. So what it does is the clients will try to load its previous local model. So usually at the end of the local training, whatever is the model we obtain that we send to the global server, it usually keeps it in memory. It does a local storage of it. So in the next round, it uses this particular previous round's local model as a starting point to do the training here. Now, how does that work? Is first, there is something called as the partial loading strategy that this paper follows. This is the core idea of the paper. The ATC is nothing but a strategy for this particular round for this particular client. And the strategy can be roughly thought of as this way. Let's say if the strategy decides that for any parameter, this has to be 0, then we will load the local model for that particular parameter. So in your weight matrix, we'll start entering parameter by parameter. We go with each index. If the first one says, the strategy says it's better to be 0, then we load the local model. If it says it should be 1, then we load the global model. Now, how the strategy is chosen, I'll come to it in the following slides. But basically, the strategy kind of determines what should be the, how I will be initializing the local training. So I would do that and do this partial initialization, and then we continue to do the regular training. And at the end, whatever model we obtain at the end of the local training, we send it to the server as well as have it on the local storage. So this is a skeleton of the paper. So now going to how we try to choose the parameters and how do we do the strategy, it follows two methods. First algorithm that the paper proposes is called the PartialFed fix. Here, it tries to manually come up with strategies which could be best for your given network, for your given client, and for the data that it has. So it goes by some prior information or some expert knowledge that we have about the network architecture in general that we know from before. So it uses some of the strategies like that. The first thing that they say is the feature extractor, classifier, separator. So basically, if this is your ResNet 18, you have several stages, like stage 1, stage 2, so on, and the last is your fully connected layer. So the different strategies can be like bottom-up sharing, where the bottom layers of your model are shared, or you can do the top-down sharing, where you can start sharing the common parameters from the topmost layers coming down. So what do I mean here by bottom-up and top-down is that when I have a global parameters that is sent by the server to all the clients can choose to keep the bottom layers as the global parameters, and for the other layers, it can keep its own local model like this one. So here I could say that ATC is equal to 0 for upper layers or the upper stages, higher stages, and you can do it as 1 for lower layers. So that way I can load most of the global parameters for the bottommost layers. And then on the topmost layers, I'll go with the more local model. This would be bottom up, and doing the reverse of it would be top down. So the authors try to do this experiment on a ResNet 18 model, and they use a data set called home office, and they try to see what is the result. Here, load means which layers load the global model. S1 means S1, the first stage of layers are, of all the clients are using the global parameters, the rest of the layers are using local parameters. And S1 to S2 means two stages are using global, so on. So if I say full, which means that all the stages and all the layers of your ResNet are using just the global parameters, which means it's just as federated averaging. And the other columns over here, P, A, C, R, these are nothing but just the tasks, the classes that this Office Home data set has. It's called clip art, etc. I'll explain about what this data set columns are, maybe in the experiment section, but basically, these are the kind of results for each of the subsection of this data set. And this is the mean value. So we see that the best accuracy is obtained for when you go bottom up, and especially when you use from the bottom going up to probably the last layer. But if you leave out the fully connected layer is when we see that the best results can be obtained. So this is one observation. So this is the first method of probably using this feature extractor classifier separation to say which layers should have global parameters. The second,
Pavana, could you go
yeah.
to this one? Is this like empirical one, and based on the empirical trials, they give some observation, or is there any specific explanation behind this? It
Okay.
seems like, yeah, I do understand your motivation, right? So for example, although I don't know why you divide that by layers, but still, some layers you use a global parameter, some layers you use local parameter, then you do the training, potentially it give you better performance. And you based on the, I don't know, you're based on this kind of weighting or something, you do the trial, empirical trial, right? This one is, look to me, it's more like an empirical trial. Try one layer, two layer bottom up, three layer bottom up, then see when you have the best performance, something like that, right?
Yes. Okay, so there are two things in this. One observation is, yes, this is kind of little empirical at this algorithm. They propose several strategies. I mean, in the starting, they give more very naive approaches, which can be used. And eventually, they'll explain more methods which are more data-driven and which are more adaptive. This is a very naive approach, the first one that I'm explaining. And this is kind of more empirical. The intuition is just that in the lower layers, you see that it is closer to the input data, which means that the training should have just begun. And you need a lot of knowledge to keep on improving your local training. So that's why it's better to use the global parameters in the lower layers, so that you kind of have the aggregated knowledge from several clients. So you gather more information in the beginning, and so you do good job in training. And eventually, as you go to higher layers, you focus more on your own local data set, more on your local parameters. So that's how it contributes to the accuracy. So this is kind of empirical and kind of tested in the more neural network way at this point.
Okay, thank you.
The next commonly used method is the batch normalization. So what is the observation that this paper is trying to tell is in using batch normalization is that from previous work in the literature about batch normalization, it is an established fact that using the batch normalization layer is not very, if sharing the batch normalization in lower layers for if you have non-IID data does not yield very good result. So you are better off to not share your batch normalization layers. So to keep local parameters instead of global parameters when you have batch normalization. So they just try to do the experiment just to emphasize the fact and see that that's how it works. And especially when they apply their algorithm of doing the partial training, partial local global split. This is the result again on ResNet 18 on the same data set. You see the observation is if you do not use the batch normalization layer and if you do not share the fully connected layer, then you have the best accuracy. So this is another strategy that can be used along with doing the partial federated averaging, and you can even use this kind of strategy to obtain good results. One other thing is this ATC value in this. So the ATC is nothing but your strategy. What is the strategy that you use? So this partial fed fix in general uses this, that if you have a fully connected layer, then the value should be 1, which means you do not share it. And if it is 0, for other cases. So it's better to share the lower layers and do not share the fully connected and the batch normalization layer. So this is kind of intuitively how they do. And the other knife approach is to use the skip loading. So the skip loading, as we know in ResNet, is let's say that you have several layers of your several convolutional layers that you have. They can be kind of grouped into stages. And let's say for simplicity, we rewrite them using alphabets, A, the small a, B, C, D, etc. And here is your input. And the last one is your fully connected layer. So this is how your ResNet is partitioned. So what they do in this method of partial training is they'll first take AA and BB, they load it with the global parameters, and eventually they'll, for C and D, they will load the local parameters, and they'll show what is the accuracy result on each data set, on each of the tasks that you have. And this is how they keep doing. One observation is that you do the adjacent layers, and then you skip some lower layers, you skip some stages, and then you go to the next layers and then next stages. So we keep doing that, and in the ABCD or the ABCD, we see that A is taken, the small a is skipped, B is taken, then this B is skipped. So for each stage, you're only considering one of it instead of considering all of the layers inside. And you only load those with the global parameters. And you see the observation is that by doing this kind of a skip loading, the performance accuracy is much better. So the skip loading in combination with this partial federated concept seems to yield a very good result. So these are some of the strategies that this paper first proposes. So all the 3 methods that we saw so far, whether it is the top-down, bottom-up approach, or the batch normalization, or the skip loading, these are very static in nature. We see that they're, first of all, more empirical. They do work, they have good accuracy, but they're very empirical. And how do you keep choosing the strategy for everything? Because every strategy that you choose will keep changing with the task. It will keep changing with different data. And if you use a different architecture, network architecture, then you have to re-strategize everything. You have to manually sit and see which is better, and you have to do the strategy. So it's really hard to choose. Plus, this is a very naive approach, as I said, mainly because the complexity is really hard. If N is the number of devices you have, T is your number of global iterations, and K, let's say, is your number of layers, the complexity is really, really high. So while this approach works, a more better method that this paper proposes as an extension of their own previous algorithm would be the partial fed adaptive. So what you do here is you try to learn the initialization strategy automatically instead of going with, excuse me, going with some fixed strategies like this. You will do more automatic way to do an adaptive approach. And here they have a data-driven approach to adaptively choose which parameters should be loaded globally, which should be loaded locally for a given specific client. In that, they use 2 things. One is the Gumbel softmax. Why do they use a Gumbel softmax? Is because the adaptive strategy that we were choosing so far, our A over here, you will see that it's more discrete. So the decisions that are taken are very discrete. But
I have a question about previous slides. You show us several strategies to choose what to load or what to escape, and here you gave me the table, the mean clump. Is that the result for one trial or several experiments?
Okay, so for example, this one, right, the first row, the last value, this will be for the whole experiment, but on different classes. So this data set, the office home data set, in itself has 11 different smaller data sets in itself. So different domain, you can say it as a multi-domain data set. So this is for each of these results are for each of the domain P, A, C, and R. And the mean would be the average of these things. So this will be at the end of the training.
Oh, I see. So PACR are for different domain or tasks.
Yes, exactly.
All
The
right.
main task is
So
classification, but yeah, they're
yeah.
different things.
So for example, for each atom, like the first one, 89.57, this is the result for one trial or another averaged one.
No, this is you once you finish this is basically the test accuracy.
Yeah,
If you were-
I know.
Yeah.
Because I raised this question because we can see some difference among different experiments uh, uh, regarding to their different initialization, but the difference is a little bit close. And so I'm wondering whether it's due to uh, the experiment trial. For each experiment, you will get a little bit different results due to your even in our traditional training, different randomly initialization will give you some results. You will have a variance about the accuracy or other metrics. So I'm wondering if if each accuracy or atom from this table is only the result for one trial, it might be not um, reasonable to say that which strategy is better because we can accept some variance. So
Okay.
that's why I asked.
Okay. Yes, your question is really valid. The results are quite close, no matter which of these sub-strategies that you try to use. But these results are from the converged result. So this is the top one accuracy that they measure after the training and when you propose the test data to your system. After it uses this kind of skip loading strategy for each of these load method, what will be the converged result and what is the top one accuracy you get is what is written per domain in this table. The result is quite close is because we have literally we are using the same model, but just that we're just probably skipping one layer or maybe we're just considering the adjacent layer or not. That's why you see that the end result is quite close to each other.
Yeah, I see. So I'm sure. I really appreciate their efforts to to conduct those extensive experiments to see whether there is a pattern to find the optimal strategy of this weight loading. Uh, but the difference still, this improvements or the difference between the best one and the worst one is not quite that huge to persuade it's worthy to designing this strategy, initialization strategy. So I just want to make sure that motivation is valid and it's strong enough to continue.
Okay, yes, your concern is really valid. Maybe like if we look at okay, maybe if we look at this previous table where we have the result of the full, which is nothing but the fit weighted averaging, where instead of doing the partial initialization, you do the complete global model initialization, right? So here we see that the accuracy difference is quite a lot. Like it is probably, if you can take this clip art domain data result, for the federated averaging, you have about 65%. And by using the partial learning and by employing the sub strategy of using without batch normalization and without the fully connected, you see that the accuracy has jumped to almost 74%. So I think this way you see the motivation can be seen strong, because if you have multi-domain data sets, doing the normal federated averaging was probably not going to fetch a good result. But instead, if you do this partial federated averaging, federated learning, and probably use some sub strategies as stated in this paper, I think we can achieve a better result.
I see. Thanks. You can continue.
Okay, thank you. So going back to the other proposition of this paper about using adaptive partial fed instead of using a fixed strategy. One is because we have discrete decisions that is made and which is not differentiable. Because they want to use a data-driven approach, they first try to use the Gumbel softmax to make sure that the process becomes differentiable, and then you can continue to use traditional optimization algorithms such as stochastic gradient descent, etc. So that'll be the first thing. And the next thing they would try to do is what kind of sampling strategy to use. A little bit following from the previous slides where we were doing the sampling of the whole ResNet, there are different ways that you can set the granularity. Either you can do the sampling based on the stages, or you can use the blocks, the ResNet blocks, or probably you can just go layer by layer, convolutional layer, then the fully connected layer, the whole layer-wise concept. So what is the thinking behind doing this is just that you can know whether you have to load global model parameters or local parameters. And for example, if I choose that I want to use stage for this, then all the excuse me, all the clients will group their parameters in one stage. Like, so if I go to client one and if I say do stage wise, then all the it will try to group the whole parameters in each stage together. So when I try to use a strategy, apply a strategy, it will go stage wise. So it will start applying to stage by stage. And this is much easier to control and easier to define how to do the adaptive strategy. So eventually they'll use the EM-like strategy to update this iteratively. I'll explain that again. So this is the main thing that they, instead of using a fixed strategy, they move to a more data-driven approach and they try to do some modifications to accommodate that. So now the architecture would look something like this. Here you have your global server and you have the clients. We are trying to target the partial initialization for the local training in each of the client. And inside each of the client, now how we try to do the strategy of choosing the initialization is, let's say all the yellow blocks are your global parameters and the blue blocks are your local parameters. First, we have to do the parameter selection that which will be chosen where. So first we'll choose what is the sampling that we'll follow, whether you want to do layer wise or stage wise, etc. So once that is decided, we go for a Gumbel distribution so they can then be added together. And then here we can leverage the Gumbel softmax by introducing the temperature parameter. And this is nothing but our softmax computations. So at the end of this, at the end of this softmax, you will get the soft probabilities as your output. They see that through a PyTorch documentation, they saw that using a hard sampling trick is much better because at the end, you will get back to the discrete values, which can be used here as a sampling strategy. We can use the same ATC from our algorithm, and we can use that to do the parameter selection. And in turn, this is how it will get selected. For example, if I took stage-wise, probably the strategy said use the global models in the first stage, then local models, so etc. So according to what the strategy chose, this will be a more automated way, depending on your data distribution, depending on the kind of sampling that you chose. This is how we can more adaptively choose your initialization strategy. So explaining this in an objective way, this will be the main objective that the system will now try to minimize. So for each client C, the loss function, the training loss L train per client will be in this way, where we try to minimize the loss function using the adaptive strategy. It is easier adaptive strategy vector and your weights. And with respect to your data, because we are trying to look at more data driven, because the main focus is that you have non-IID data and it's very difficult to have convergence and you want a more personalized model. So that's why you're looking at the data dependency here. And this is mainly submerged on the initialization strategy that you choose over here. So whatever strategy is chosen, that is kind of put over here, and then we try to minimize this whole thing. And like I was saying, for doing the differentiable training, because we want to use the Gumbel distribution, we try to do the reparameterization, just like how we do the reparameterization trick in our neural networks. We use the same concept so that we can make this whole thing differentiable. And we use the standard softmax Gumbel distribution formula to come up with a new strategy. So some of the parameters over here in this formula are, one is G, which is your standard Gumbel distribution, which has this kind of format. U is your uniform distribution, which is sampled IID. And alpha is your distribution vector. Now this is a vector which is new. This will which will define the probability of loading the global or local parameters. So this distribution vector will tell us the actual strategy. And tau is your temperature parameter of the softmax. So using this kind of a formulation, we can come up with UTC. The paper mentions UTC over here, but even this is nothing but the ATC itself. They just use two different words. I mean, they use U over here basically to say that it was a little different compared to the previous slide. And eventually, to do the hard sampling over here, because at the end of this, you have the softmax distribution. So you have soft labels coming out. And because you want a more discrete strategy, so you will use the hard sampling trick to obtain a more discrete sampling by using this kind of a formula where y soft is nothing but y is your label and is soft as your soft label. And using that, you try to come up with your hard label. So this is how this can be implemented. And explaining the whole process in an algorithmic way, the things on the server remain the same. The server try to just do the aggregation of all the local models and do the broadcast. Inside the client, a little bit different what will happen here in the adaptive way would first you initialize the alpha over here, because that will help you to choose your initialization strategy. And then you do the sampling based on this equation. So once you do the sampling of your strategy, you compute the weight vector according to that, whether how much of it you will choose local parameters, how much of it you will choose the global parameters, and then you continue to do the model parameter update. Here we try to do two things. One is to do the model parameter update, and the other is to keep changing this alpha, because we want to adaptively choose this strategy for every client for every round. So we will try to iteratively try to solve these two things. And at the end of the training, we will sample whichever was the best parameter according to the alpha, whichever was the best W. We return that W to the server, and we also keep a local copy of this. So this is how the whole training will continue. It's just as federated averaging, just a couple of more steps would be probably to have this kind of different initialization strategy, and how you do the update and send this update to the server. This will be a couple of more steps that would be added. I next have the experiment. If you have any questions so far, please you can feel free to stop me. So this paper does some simulations on two different tasks. One is your classification task. The main highlight is doing the cross domain, because that is the motivation of the paper, that federated averaging and the existing methods, existing personalized federated averaging, federated learning methods do not perform very great when you have cross-domain data. So they focus on cross-domain classification task and the cross-domain detection task. And for each of it, they use two different data sets. One is the office home data set, which has 4 different domains under them: the art, clip art, product, and the real world. These are the abbreviations which we used in the previous tables. And for this, they use a ResNet 18 model. And for the detection task, they use a more challenging data set just to show that their method indeed works better than the existing methods. Use a more challenging data set of UOTP, which in itself contains 11 different detection tasks, each of them having different data size, each of them of different domains and different categories. For this, they use the SE ResNet 50, the squeeze excitation blocks enabled with the ResNet 50. And for the baselines, they use the federated averaging, the classic federated learning algorithm. They use FedProx, which is another very popular federated learning for non-IID learning, which uses a proximal term for doing the training. And the FedBN is the one which uses the batch normalization. And PFEDME is a personalized federated learning paper from old NIPS conference, which uses the Morio envelopes. So these four are considered as the baselines. And for the cross-domain classification task, here is the results that can be obtained. On the left, you have all the methods. When I say single, it means that what is a single domain result, like what is for P, what is for A, etc. And all means when you train each of the clients with all the domain data, like you will train it with P, A, C, R all together and take an average of it. And these are the four baselines that we just explained. And for this one is the partial fed fix, the more deterministic strategy that we explained first. In the first one, they have the top down, bottom up is S1 to S4 layers. And the next one was the batch normalization, without batch normalization and without the fully connected layer. And the third strategy was the skip connection, where we took ABCD, we took the alternate ones and we left out the adjacent ones were skipped. And this next one is the partial fed adaptive, which is a more data-driven approach of finding an initialization strategy, where they took stage-wise, block-wise, and layer-wise as different sampling methods. And for the home office, the top one accuracy seemed to be this way. The ones in red means those were the best result, and the ones in orange means the second best result for a given domain task. And we see that for all the, on average, we see that like the partial initialization surpasses all other methods, all other baselines and all other single methods and all methods. We can kind of conclude from this that naively sharing all the model parameters and doing the training from the whole global model probably is not really worth it. Instead, we can use more simple strategy like this paper proposes to enhance our accuracy in a much better way. So for example, here, Fed averaging on Fed blocks for this particular domain data, we see that it has a drastic difference of 67 and 72 compared to the baseline's state of the art and this paper. So for each of it, we see that the result is much, much better. And then we look at the detection task where the cross-domain detection is done. Here they use the UODB dataset. Like they mentioned, this is probably a more challenging dataset because they have different kind of data from probably images from the kitchen to your medical images of brain deep lesion, and you have some comic characters. So you have very different domains and very different varied kind of data. And even in this, we see that the top accuracy is much higher for the methods proposed in this paper. The single was again using the conventional approach. These are the three baselines. This was without SE, without the SE ResNet method, and this is without the batch normalization, etc. And the ones marked in red means they are the highest values. The orange is the second highest values, and the data sets marked in blue means these are supposed to be more challenging data sets. So the detection is quite hard in this. The DL is like your deep lesion, your medical images where the accuracy is really low generally. So we see that compared to even other data, when you have more challenging data sets like these, the proposed method in this paper really outperforms all of the state of the art. This is about how the performance is. Next, they talk about how the strategy analysis varies. Like how does this initialization keep changing throughout your training, through your number of iterations. So on the x-axis, I have the iterations, your federated iterations. And on the y-axis, we have the probability of loading the global parameters. So probability of loading global parameters being high would mean that all the clients are initializing a lot of global parameters. So which means that they're sharing several layers of it. And from left to right, we see that what is the behavior for every stage. If you use stage-wise, you keep going loading from down, bottom up, and this being the last fully connected layer, what the behavior is like. So the clear tendency we see is that in the initial iterations, most of the clients for all the different domains, they're all sharing the global parameters. This is kind of in line with the intuition that in the initial rounds of the training, the client really needs the knowledge, needs an information from several different clients. It needs a lot of more information than the local model itself will produce. So that's why it probably takes the global model, global parameters in the initial rounds of the training. And once it gets better and better, it uses lesser and lesser of the global parameters and uses more of the local parameters. So it has a more targeted, focused, customizable model at the end. So, and the other observation in general about how the bottom-up approach is much better and is quite seen over here. So in the initial layers, we see that more of the sharing of the global parameters keeps happening. And eventually, like if you go probably to stage 4, you see that only in the very few rounds, this global model sharing is happening. Like even after probably the 10th iteration, we see that most of the clients do not use the global model, but instead they start focusing on the local parameters, and that will yield much better accuracy. Except the exception in behavior is the one that is pointed in the red box over here. While all the other domains over here, like clip art and product, are kind of adhering with the observation over here, just the one with the art, the blue one, it is showing a little different behavior, that it tries to share more of the global parameters continually in opposition to others. This was probably because according to this art dataset, the observation by the author is that it was more challenging. The art dataset is more challenging. It is very, very varied. So that's the reason it continues to share even the fully connected layer to learn more of the global data parameters and then to do the local training. So this is just one exception that was seen in terms of behavior. But overall, the tendency of sharing the global parameters or the local parameters has been this way. And this same observation was nothing but the result of these things. It's just that the strategy parameters were just plotted over here to see what is the behavior. And we see that different knowledge is usually acquired at different training phases. And also, again, the initial training rounds will choose more of global parameters, and eventually we focus more on the local information. So this kind of strategy works much better when you have cross-domain data. And the advantage of using this method is, again, that you can learn client-specific strategies, and you can relieve the client from any negative impacts that will probably be caused by any distribution shifts and a lot of non-IID data involved in training. So these were the experiments, and here I have the conclusion. So we demonstrated a partial fed method, which is more focused on a personalized fed-weighted learning, which partially initializes the client model from global parameters. It uses its own strategy to do that. One method is the partial fed fix, which empirically selects layers with some prior expert data that information that it already has. And the other more flexible one was the partial fed adapter, which automatically learns the selection of what kind of initialization parameters should be used and which works better. And overall, they validate their algorithm on several benchmark data sets, and they get some state-of-the-art performance. So was my presentation. If you have any questions, please let me know. Thank you.
Any questions?
Oh, I have some questions. First about their adaptive measure. Could you go back to the slides?
Mhm. Yeah.
The next one. Yeah, here. Basically, they proposed a sample strategy to adaptively select the layers, right? The weights. Here, what's the logics here?
Oh, the logic?
Yeah, the logic.
Oh, logic is like your vector which comes out at every stage, which has the information about your feature extraction, and which will help you to make the decision of your classification at the end. So logit is kind of the vector that comes out at every stage.
And here you use the stage to denote different layers.
Yeah, this stage consists of several layers
Several
internally.
layers, yeah.
Yes.
So you need first to assign a logic and through a distribution, it will give you some sampling strategy, right?
Yes, most of it, yes, but you don't choose the logics. You just have to decide whether you want layer wise or stage wise, etc. You just have to decide that in order to do the sampling.
So what I don't understand is how those logics are generated. It's assigned or is generated by the results or by the some information from this training process. I'm not sure this part.
Okay. Okay. Logics is usually generated when you're doing the training. It's like how you have the gradients that get generated. Logic is just this intermediate vector that comes out in between the training, which will, this logics is what will be used eventually, which will go to the softmax layer. And then the softmax will look at what the logics was, and then it will try to do the decision. Fully connected layer will do the decision based on this logics. Logics is just it's, you can imagine it as the weight or the, before the weights and the gradients come out, you have these in between vectors that get generated during the training, right? It's that we don't have to do any kind of manual way of generating it. It's just that when you do the training of the neural networks, they just get generated. Like how you have feature extraction vector, right? Yeah, logic is it's like almost like the feature extraction vector.
Yeah. So where do they where do these logics appear in their algorithm?
Okay, so these
Just a logarithm, right? Some alpha or some.
yes. Actually, it this logic eventually gets translated as your weight. So if you have to look at the algorithm, when you're doing the training, you generate the weight, right? This W. Before we reach this W, you do the sampling of the batch and you start the training, right? In the middle, you will get the logic, your feature extraction vectors, and that will go into your softmax. It will go to your fully connected layer like this. And in the end, you will get the final vector of 0, 1, the classes, the decision. So it'll be somewhere in between. You will not see it in the algorithms generally. The algorithms will only talk about the final weight. Yeah, logic will probably come like somewhere in the middle.
So, oh, I see. So the logics are outputs of each stage, right?
Yes.
And yeah, I see. So another question is about this distribution. How do they decide which distribution to use? Because seems like they use a distribution, not networks or something to nurse some weights from these logics.
Right. So at the moment, they are just using this. Yeah. For the standard Gumbel distribution is what they're using. And inside of that, they're trying to do the sampling using the uniform distribution, and they do IID sampling. But for future work, they want to explore different kind of distribution inside this. But for now, they're just using that, this kind of sampling.
So what are parameters of this sampling strategy? They need to update.
For the sampling strategy?
Yeah, because that's a adaptive Oh, so here is this adaptive means they just use this some distribution to sampling the logics and to decide the weights, not to know how to use these weights, right?
Okay, so how they do that is just to select the parameters. They just try to minimize this kind of loss function. For that, they try to look at the data of how the data distribution is on each of your client, and they try to do this whatever you were just the way you understood is right. All this sampling strategy and all of that will come as part of this whole initialization strategy, and that is how they will be able to choose which parameters should be selected, the global or the local, for which stage, for which layer, etc.
Mm. All right, that's my question. Thank you.
Okay.
Oh no, did they mention, I mean, this design, it seems to work, right? But sometimes it did not give the best performance. Do they mention, so say, if we have some other sampling strategy, for example, the random sampling, right? Is it going to give us better performance or potentially give us the worse performance? Or say probably we can replace the sampling strategy they propose here with some reinforcement learning or something, right? So we can make a better combination of local layer and global layer, right?
Okay.
Government,
Yeah, that
they propose approach, but they didn't provide the justification why this one, performed good. Is there any room for us to improve?
okay. Yeah, that's a valid question. So they just they don't go exactly comparing what every sampling strategy could have an impact on the global model. Actually, it does, right? Like what you said is right. The
Yeah.
way I decide to do sampling here will decide my initialization that will have an effect on the final global model or the whole end result. What they say is they want to explore combination of different strategies here as part of the future work, because they say that there's a scope to try different methods here and explore the impact of it. But yeah, they just have a discussion section. They say that they want to do this in the future work.
So the major thing they want to sell is, their observations say if you mix the global layer and with some local training layer, it gives better performance for personalized training, right? That's the major point they want to sell.
Yes, yes, absolutely.
But in terms of a strategy, I think it just provides certain kind of observation, even for this one.
Mhm.
It's just like, I don't know, it's one of them, right? Probably based on this, you can propose many this kind of sampling strategy.
Yes, yes, totally. Yeah. This is one of the first, you could say. I think eventually we might see more of the partial federated learning papers, like maybe how we had meta learning and few short learning. Maybe this can serve as a new sub method of federated learning. Probably that's why NIPS, it was published in NIPS. Maybe, yeah, I think there's a lot of scope to build on top of this, I feel.
Yeah, but that doesn't inspire us. How about this? Did they talk about, hey, for example, say we don't divide by layer, like say, let's divide by round, right? For example, for the first a few initial rounds, we use the global layer to train that, right? Because like you mentioned, the motivation is, I mean, at the beginning, probably we need more knowledge or to train something. But when it close to the convergence or close to your own loss function, personalized loss function, then you just use your own layer. I mean, you use your local training. You don't share. You don't do the global stuff, right? If we divide by time, this one, if you compare this one to the wireless communication, right? So this one is like FDMA, right? What I'm proposing is TDMA. You know what I mean?
Okay. Yeah. I see that.
You divide by the time domain instead of this kind of layer domain.
Right. But it's a good idea, Dr. Pan. But I think the problem would still go back to if I use the first few rounds of just probably global training, it's probably not. It's they claim that it's probably not efficient because you do not need to use all of the global parameters even in the first few rounds. Even there, you can start mixing some of your local parameters. You can probably converge faster. You will get to your personalized model maybe in fewer rounds.
But no, I mean, I just, you know, the intuitive proposal, right? So you can do more complicated, say, we have OFDM in wireless, right? So you can come up with, I mean, you can combine the TDMA and FDMA. Like here, you can combine the layer approach and the time domain approach to generate like more OFDM approach. You know what I mean? Then probably you can borrow a lot of knowledge from Dr. Joe, who has been working on the physical layer for a while. You know, so there's a lot of design there, and those designs are very mature. Then they're going to use the resources efficiently. I mean, if this is the observation, probably, I mean, the wireless people can do a lot for this.
Yeah, it looks like.
You know what I mean, right? If you put it into 3D, right? The time is a layer. You can do like OFDM allocation. Probably they're going to further accelerate the training process.
Yes, I think so.
Yeah. But this one's interesting. People just talk about, you know, pruning the parameter stuff. Nobody talk about the mix the layer things. I mean, as far as I know, probably some of you guys read the paper similar to this one. Okay. How about if you further combine this approach with the pruning as well? You just prune some parameter. Probably it's more efficient. Do you think so?
Yeah, I think it's a good way to find a pruning strategy based on this result, I think. Because maybe if you can just do a few rounds of training, you can easily determine what is the sampling strategy that works the best. And then maybe you can do the pruning as part of that, and then you can have a smaller model and faster convergence.
Yeah, also I have a follow-up question related to the pruning, right? So for pruning, we understand the basic unit is the parameter, right? So like the weight or something, you prune some weight if it's closer to 0 or something, right? So you keep those weight if they're play important role in the training. This one is like a little bit higher level. It's not based on the parameters, more based on the layers, right? So when you try to, I don't know, is there any kind of trade-off of complexity in terms of you do the layer selection or you do the parameter selection? I think my question is, why don't you like just use the pruning? You know, you pick up some important parameter for the training instead of you try to mix the layer stuff.
Okay, this is mainly because you want personalized models. You want to more customized kind of models in every client. That's why they try to do the mixing. But as well as pruning is where you're more specifically looking for maybe acceleration or so smaller energy inference, or so that's why probably these both differ.
No, actually, when you do the pruning, you can still do the personalized pruning, right? Based on your training, and you can say which weight and the parameter is important.
Yeah, they can be combined like that. Yes, I think it should be doable.
Yeah, I think,
go ahead.
I think the parameter in each layer I don't know. I mean, for here, if you choose a different layer, you still follow the same structure, right? The only thing you choose is, for example, the yellow layer's parameter is different from the blue layer's parameter, right? But,
Yeah.
but from the general machine learning model structure, they're the same, right? So we're
Yeah.
still talk about the parameter here. I mean, by choose a different layer, you talk about, okay, I choose a group of different parameters. So the yellow one is a group of global parameters. The blue one is a group of local parameters, right? So
Right.
instead of doing this, my question is why don't we just follow the traditional pruning? You know, we basically based on the weight of the parameter for a basic unit, right? Instead of the layer for a unit.
Okay. Okay. I see what you're saying.
Yeah.
Yeah, I think it's an interesting idea to explore. Using the model pruning, we can if we can precisely identify what the parameters are for the global model, global pattern, and what the parameters are for the personalized patterns.
Yeah.
And then if we can do some pruning and selectively pruning,
Yeah.
we probably can improve the model quality.
Yeah, I think
Yeah.
previously
Yeah.
people only use the pruning for the training efficiency, right? They never think about, okay, we can use the pruning, I'll say the personalized pruning for the personalized training, right? So like Dr. Wang mentioned, if we can combine this idea with this paper,
Mhm.
yeah, probably yes. I think it's even further improvement. I mean, this one is big. Again, this one, the basic unit is a layer, right? Pruning basic unit is a parameter. Layer, from my understanding, is just like group of parameter, a layer of parameters, right? If you follow the same structure. So why don't you use try pruning, say if you, for the personalized learning? I think that would be.
We have a similar idea, but it's not a pruning, it's similar. So the idea is we have a mask for each client. And this mask will be try to keep the local parameters out of the aggregation. So if the parameter can pass the mask, then we would say this is for global patterns. And during the training, we also adjust the mask. So each client will have a mask. Eventually, if we during the training, we adjust the mask for each client, then gradually the mask can probably, can select the global parameters and leave the local parameters.
So,
But we are not doing the pruning here. But if we can do
is it similar to the on-lease idea? You know on-lease paper, right? This is the mask for further learning or something.
Oh yeah. It's similar, but that paper, if I remember it correctly, that paper only train the mask. That paper doesn't train the model itself.
Yeah. I don't train the mask. Yeah.
Right. It only trains the mask, right?
Yeah. Then it's the mask because they're targeted at personalized further learning.
Yeah. The paper named like a Fed mask. I remember.
Yeah, communication efficiency too. So
yeah.
So you guys mask also train the local model?
We train the local model and also we train the mask together. Yeah. The paper was I think it was rejected by the CVPR and we resubmitted it.
Okay. Yeah, Pavana, probably you can further discuss with Dr. Wang and Dr. Wang's students in this area to say if we use the pruning for the personalized further learning, is there any more things we can do?
Right. So that student is still trying to explore how to distinguish the parameters for local patterns and global patterns.
Well, I mean, if we cannot find very theoretical way, we do something similar to this paper. Just do a very intuitive, just try to sell our idea. You know, we prune the parameter for the file learning. Yeah.
Yeah.
Okay. Any other questions or suggestions?